Welcome. In today's session, we will look at ketone bodies. And under ketone bodies, by the end of this session, you should know ketogenesis, that is how ketone bodies are produced in the liver. KETOLYSIS, that is the utilization of the ketone bodies by the extrahepatic tissue. And we will also look at diabetic ketoacidosis, which is found in type 1 diabetes mellitus. So welcome all. My name is Waris Munyere and I'm the Ure Daktari. So give me a minute. Let's us also hide this. Okay, now ketone bodies. The liver mitochondria have the capability to convert acetyl-CoA, which is derived from fatty acid oxidation, into ketone bodies. Now, ketone bodies include acetoacetate, 3-hydroxybutyrate, which is also known as the beta hydroxybutyrate, and also acetone. But acetone is a side product, is just a side product, okay? It's a side product of acetone, acetoacetate, sorry. Now, only two functional ketone bodies, acetoacetate and 3-hydroxybutyrate. These are the functional ketone bodies and they are organic acids, okay? Acetone is non-functional. It's a non-functional ketone body. It is just a side product of acetoacetate. Now, acetoacetate and the 3-hydroxybutyrate or the beta hydroxybutyrate are transported in the blood to peripheral tissue, where they can be reconverted to acetyl-CoA, which can be oxidized by the tricarboxylic acid cycle, okay, the Krebs cycle. Now, ketone bodies are important sources of energy for peripheral tissues because, one, they are soluble in aqueous solution and therefore do not need to be incorporated in lipoproteins or carried by albumin as other lipids. So the means of transport from the liver to extrahepatic tissue, it's easy, okay, because they are simply soluble in aqueous solution. Now, another one is because they are usually produced in the liver during periods when the amount of acetyl-CoA present exceeds the oxidative capacity of the liver. When is the amount of acetyl-CoA in the liver? In which periods is the amount of acetyl-CoA present in the hepatic tissue exceed the oxidative capacity of the liver? One, when fasting. When fasting, the amount of acetyl-CoA present will be higher. Another one is in people who have insulin deficiency, okay? That is in type 1 diabetes mellitus. Also, they are usually used in proportion to their concentration in the blood by extrahepatic tissues, such as skeletal and cardiac muscle, the intestinal mucosa, and the renal cortex, such that even the brain can use ketone bodies to meet its energy needs if the blood levels of ketone rise. If the ketone in the blood rises, even the brain will use those ketone bodies to derive its energy, okay? So let's look at ketogenesis now. During a fast, okay, the liver is usually flooded by fatty acids, which are mobilized from adipose tissue. That is obvious. In the adipose tissue, your triacylglycerides will be broken down to produce your fatty acids. Fatty acids will be incorporated into the high density lipoproteins and be transported to the liver. Now, once in the liver, they undergo oxidation to produce acetyl-CoA. Remember how fatty acids were being broken down into acetyl-CoAs. I hope you have watched the video. If you haven't, I have done a video on how fatty acid oxidation, the 4 steps. Please remember: first, dehydrogenation, which is FAD-linked, then hydration, then second, dehydrogenation, which is NAD-linked. Then we have the cleavage step. Then you produce a fatty acid which is 2 carbons shorter, and acetyl-CoA. Please watch that video. Then, now, the resulting elevated hepatic acetyl-CoA produced in fatty acid oxidation inhibits. Now, acetyl-CoA will inhibit the action of pyruvate dehydrogenase, but will activate the activity of pyruvate carboxylase. Now, pyruvate carboxylase, remember, will convert pyruvate directly into oxaloacetate. Okay, so the oxaloacetate produced by pyruvate carboxylase is used by the liver for gluconeogenesis, okay, rather than for the TCA cycle. Now, additionally, fatty acid oxidation decreases this ratio between NAD and NADH. How will it decrease? Because the NADH will rise, because remember, we have the second dehydrogenation step, reaction number 3 in fatty acid oxidation, the one which is NAD linked. So more NADH will be being produced. When that ratio decreases between NAD and NADH, there will be a shift. Remember, myrate is usually converted to oxaloacetate by the myrate dehydrogenase. Now, in that reaction, we will put in an NAD and produce NADH. Now, imagine a situation where NADH are more. This reaction will reverse. It will move to the left. It will shift to the left. Okay, so more oxaloacetate will be produced. Sorry, more myrate. Okay. Then now the decreased once oxaloacetate is converted to myrate, there will be a decreased availability of oxaloacetate, which is required to condense with acetyl-CoA, and this will result, because now the acetyl-CoA won't they can't combine with the oxaloacetate to form citrate. This acetyl-CoA will be used for ketone body synthesis. Okay, now acetyl-CoA for ketogenesis is also generated by the catabolism of ketogenic amino acids. If you have done the amino acids, you will notice that we have strictly ketogenic amino acids are 2, lysine and leucine. Then we have the amino acids which are both ketogenic and glucogenic. You are tyrosine, phenylalanine, isoleucine, tryptophan, those. So from those amino acids, you also can generate ketone bodies. Okay. Next. Now, ketogenesis will be divided into 2 steps. First, we must synthesize 3-hydroxy-3-methyl-glutaryl-CoA. Okay. Now, the first step, formation of acetyl-CoA, occurs by the reverse of the final dialysis reaction of fatty acid oxidation. Okay, where the mitochondrial 3-hydroxy-3-methylglutaryl-CoA synthase, or the HMG-CoA synthase, combines a third molecule of acetyl-CoA with acetoacetyl to produce HMG-CoA. Now, HMG-CoA synthase is the rate limiting step in the synthesis of ketone bodies and is present in significant quantities only in the liver. Now, HMG-CoA is also an intermediate in the cytosolic cholesterol synthesis. Remember, cholesterol synthesis, HMG-CoA is also formed. Now, what is the difference between cholesterol pathway and the ketogenic pathway? Cholesterol synthesis is a cytosolic process, but ketone body synthesis, ketogenesis, that is a mitochondrial process. The two pathways are separated by location, that is, one is cytosolic, the other one is mitochondrial, and also conditions. Now, ketone body synthesis. Now, once we form HMG-CoA, it is cleaved by HMG-CoA lyase to produce acetoacetate and acetyl-CoA. Now, acetoacetate can be reduced to form 3-hydroxybutyrate with an NADH as the electron donor. Now, not because ketone bodies are not linked to a CoA. They are not linked to a CoA. If they are not linked, they can move freely across the inner mitochondrial membrane. Okay, please note that. Now, acetoacetate can also spontaneously decarboxylate in the blood to form acetone. So acetone is just a side product when acetoacetate undergoes decarboxylation, which is spontaneous. It will form acetone, which is volatile, biologically non-metabolized compound, cannot be, it is a non-functional ketone body. The body cannot utilize acetone. Okay, that is usually detected in breath. Okay, and it has a fluidy smell, fluidy smell. It is pleasant smelling. So you will find that people who have diabetic ketoacidosis, they have a fluidy smell. Okay. Now, the equilibrium between acetoacetate and 3-hydroxybutyrate is usually determined by the NAD to NADH ratio. Because this ratio is low during fatty acid oxidation, 3-hydroxybutyrate synthesis is usually favored. Now let's look at that. Here you have your fatty acyl CoA. It will undergo the 3 steps. First, dehydrogenation, hydration. Then we have the second, dehydrogenation, to form your acetoacetyl CoA. Okay. Now, once we form acetoacetyl CoA, we will put in the third acetyl CoA, and using the reaction will be catalyzed by HMG CoA synthase to form HMG CoA, your 3-hydroxy-3-methyl-glutaryl CoA. Then this will be cleaved by the lyase. One acetyl CoA is removed to form acetoacetate. This, it can once in the blood, it can spontaneously undergo decarboxylation to form acetone, which is a metabolic dead end. Okay. Also, it can undergo reduction. Okay. It can be reduced by 3-hydroxybutyrate dehydrogenase to form your 3-hydroxybutyrate. Okay. So this is how it is synthesized. Also, you can start from this pathway, where if you have 2 acetyl CoA, they can be combined using the enzyme diurese to form acetoacetyl CoA, and we will continue like that. Please understand this reaction mechanism, please. Now, ketolysis or utilization of the ketone bodies. Now, although the liver constantly synthesizes low levels of ketone bodies, their production usually increases significantly during fasting. And during fasting, these ketone bodies are the main source of energy for peripheral tissues. Now, 3-hydroxybutyrate is oxidized to acetoacetate. Okay, remember acetoacetate had undergone reduction to form the 3-hydroxybutyrate. Now, the reverse is oxidation, and the same enzyme will be used, the 3-hydroxybutyrate dehydrogenase. But this time we will produce an NADH. Okay. Now, acetoacetate is then provided with a CoA molecule taken from succinyl CoA. Now, acetoacetate, we have acetoacetate and succinyl CoA. Okay. Now, this acetoacetate will, like, let's say, it will steal the CoA. It will steal the CoA from succinyl CoA, and this reaction is catalyzed by the succinyl CoA acetoacetate CoA transferase enzyme, also known as the diapholase enzyme. And this reaction is reversible But the product, once we form acetoacetyl-CoA, it is actively removed by cleavage to 2-acetyl-CoA by diuresis. Once you form your acetoacetyl-CoA, it is cleaved immediately to 2-acetyl-CoA. Okay, and this will pull the reaction forward. Now, extrahepatic tissues, including the brain, but excluding cells that track the mitochondria, except, for example, the erythrocytes, efficiently oxidize acetoacetate and 3-hydroxybutyrate in this manner. Now, in contrast, although the liver actively produces ketone bodies, it lacks the diaphoresis, and therefore it is unable to use ketone bodies as a source of fuel. So the liver will just produce ketone bodies, but cannot use them. Okay, so it is just producing them and not using them because it lacks diaphoresis. Okay, here we are. Now, remember, the sources of acetyl-CoA can be from amino acid catabolism. Remember the ketogenic amino acids, also from fatty acid oxidation, also from glycolysis, you can produce acetyl-CoA. Then two of them are combined. Here you have diuresis enzyme to form acetoacetyl-CoA. Then the third one is added, another acetyl-CoA is added here. And the enzyme here is the HMG-CoA synthase to form your HMG-CoA. Then HMG-CoA will undergo cleavage by the, here you have the HMG-CoA lyase to form acetoacetate. Acetoacetate can undergo reduction to form 3-hydroxybutyrate. These two are the functional ketone bodies which are be transported in the blood to extrahepatic tissue. In the blood, acetoacetate can undergo spontaneous decarboxylation to form acetone, which has a fruity smell. Then once they reach 3-hydroxybutyrate, will undergo oxidation to form acetoacetate. Acetoacetate will be combined, will take the CoA, it combines with the CoA of succinyl-CoA, a reaction catalyzed by diaphoresis, or the succinyl-CoA acetoacetate-CoA transferase, okay, to form your acetoacetyl-CoA, which will undergo cleavage immediately by diuresis to form 2-acetyl-CoA, which will now enter the Krebs cycle. Now, excessive ketone body production in diabetes mellitus. Now, when the rate of formation of ketone bodies is greater than the rate of their use, their level begin to rise in blood, condition known as ketonemia. Now, and eventually in the urine, ketonuria. Now, this is seen most often in cases of uncontrolled type 1 diabetes mellitus. Now, where the blood concentration of ketone bodies may reach 90 milligrams per deciliter. 90, but in normal individuals, it should be less than 3 milligrams per deciliter. And the urinary excretion of ketone bodies may be high as 5,000 milligrams or 5 grams in every 24 hours. Now, the elevation of ketone body concentration in the blood can result in acidemia. Why? The carboxy group of ketone body has a pKa of about 4. Okay? Therefore, each ketone body will lose a proton, a hydrogen ion, as it circulates in blood. Now, when the concentration of hydrogen ions increases, it will lower your pH. That is acidemia. Now, also in uncontrolled type 1 diabetes mellitus, urinary loss of glucose and ketone bodies usually result in dehydration. Therefore, the increase in the number of hydrogen ions circulating in the decreased volume of plasma can cause a severe acidosis. This is known as ketoacidosis. Okay, and since it is occurring in people with diabetes, it's now known as diabetic ketoacidosis, DKA. Now, a frequent symptom of diabetic ketoacidosis is a fruity odor on the breath. Okay, why? There is increased production of acetone. So the ketone body acetoacetate is very high in the blood. So most of it will undergo the spontaneous decarboxylation to form your acetone. Acetone now has the fruity odor. And remember, blood will reach the lungs eventually, and acetone will diffuse across. So once that person is near you, he will smell some fruits, a fruity odor. Acetone is also the one used by ladies to remove cutex in their nails, something like that. And I know that it smells. They can tell you the smell. Now, ketoacidosis may also be seen in cases of prolonged fasting, okay, and also in people who like taking alcohol. Excessive ethanol consumption can also cause ketoacidosis, okay. So now, in people with diabetes mellitus, we know they have deficiency in insulin. So lipolysis in the adipocytes will increase. So the free fatty acids will increase also in the plasma. And now, remember, they will go to the liver and be converted into ketone bodies. This will lead to ketoacidosis. So guys, you've come to the end of this session. And thank you for your attention. And please subscribe for more anatomy and biochemistry content. Thank you.